All right, we're still taking a look at how to evaluate limits analytically, but before we get on to the next thing that can happen, we've already seen that we want to use direct substitution and what to do if we end up with 0 over 0. But before we get to the next thing that can happen to us, we need to take a look at something like this. What happens if we had the limit as x approaches 0, let's do a one-sided limit, let's say from above, of 1 over x. All right, well notice if we try direct substitution, by the way you can do direct substitution with one-sided limits as well, we would end up with 1 over 0. And we've seen in the past, 1 over 0 is undefined, which means it doesn't have a value. So let's kind of think about this and see what's actually happening here. Well, let's say we're approaching 0 from above. That means we're approaching 0 from values that are bigger than 0. So let's let x be 0.01. Well, if I did direct substitution with that, I get 1 over that. Now remember, that's 1/10, so 1 over 1/10. We're dividing by a fraction, so we multiply by the reciprocal. So this would be 10. If I get a little bit closer, so basically I'm making one of those tables, just not writing the table. If I did 100th, again, that's like 1 over 100th. Flip and multiply, we would end up with 100. And if I had 1,000th, that's 1 over 1,000th, which of course would be 1,000th, right? And then if this keeps getting smaller and smaller and smaller, heading towards 0, it'd be what? A millionth, a trillionth, and so on and so forth. What do we get? We get a million, a billion, a trillion. So notice as the bottom gets smaller and smaller and smaller, the value gets bigger and bigger and bigger. So this is actually, as we get closer to 0, now remember, we never get to 0. 0 would be undefined. As this gets smaller and smaller and smaller, the whole value gets bigger. So this is actually heading towards infinity, getting bigger and bigger and bigger. Now notice what we got when we did direct substitution though. We ended up with this undefined statement. Anytime you end up with this undefined statement, you end up with these infinities involved because we're dividing by something getting smaller and smaller and smaller. So the last thing we got to watch out for here, if you get 1 over 0, look at you'll see what I mean by this, the one-sided limits. All right, let's go over here and look at this. Let's say if I said, what is the limit as x approaches 3 of 1 over x minus 3? Okay, since this is just a limit, the first thing we'd always want to try is direct substitution. Now notice as soon as we try direct substitution, we get 1 over 0. So as soon as you see 1 over 0, you already know that this thing is heading towards an infinity. We just need to make sure is it heading towards the same infinity. What I mean by that, remember, a limit consists of two one-sided limits. This is the limit as x approaches 3. Let's do from above, and the limit as x approaches 3 from below. Now, here's the good news. As soon as you set this up, as soon as you break this into both one-sided limits, you actually already know the answer over here is an infinity. So you can go ahead and write that. We just need to know, is it positive infinities or negative infinities? So let's think about this. Here we're approaching values bigger than 3, or approaching 3 from values bigger than 3. So if I have 1 over something bigger than 3 minus 3, is that going to be positive or negative? Well, the top's positive. Bigger than 3 minus 3 is positive. Positive divided by positive. So this is heading towards positive infinity. Here, if we're approaching values less than 3, this is 1 over something smaller than 3 minus 3. So the top's positive. Smaller than 3 minus 3 is negative. Positive divided by a negative is a negative. So as we come in from values bigger than 3, this is heading towards positive infinity. If we come in from values less than 3, it's going to negative infinity. Well, these two things aren't the same thing, right? So these are not the same. So the limit does not exist. Now, if you think about what the picture of this is, if you remember back on graphing rational expressions, here at x equals 3, this thing has a vertical asymptote, just like that. And as we approach 3 from the left side, it actually looks like this, kind of heads down like that. And as we approach this side, it heads up like that. So as we approach 3 from one side, it's diving down and heading towards negative infinity. As we approach 3 from the other side, it's diving, well, jumping up and heading towards positive infinity. Since those two limits are the same, this limit does not exist. All right, let's take a look at another one like this to see what we're going to end up with. Let's do, let's make it kind of easy. Let's do the limit as x approaches 2 of 5x over x minus 2 squared. Okay, so we're told to do a limit. The absolute first thing that we want to do is direct substitution. When we plug a 2 in for x, of course, that's going to be a 10 on the top. 2 minus 2 is 0, squared is 0. So let me actually amend this for you. If you have 1 over 0 or any number over 0, I don't care what number it is, generically speaking, most books will put a 1 there, but any number over 0, you know you're going to end up with the same situation that we were just in. So I need to break this into 2 limits. The limit as we approach 2 from below or above, I did first, squared, and the limit as x approaches 2 from below of the same thing. Now again, since we got a number over 0, we know that these are going to be infinities. All we got to do is figure out, is it positive or negative? All right, so imagine we're plugging a number into this expression that's a little bit bigger than 2. 5 times something a little bit bigger than 2 would be positive. Something a little bit bigger than 2 minus 2 is positive, squared, still positive. Positive divided by positive is positive. Here, so now we're approaching 2 from a little bit below, so like 1.9, 1.9999 kind of thing. So 5 times something a little smaller than 2 is still positive. Something a little smaller than 2 minus 2 is negative, squared is positive. So positive divided by positive is also positive. So in this case, the limit from the left equals the limit from the right. So here we can say the limit as x approaches 2 of 5x over x minus 2 squared equals infinity. Now this is one of those weird things that I personally believe a lot of textbooks have wrong. They're going to write it like this. Now, since infinity is not a value, technically you can't equal infinity unless you're working with a different set of numbers than we are. So technically they should probably have this notation. They should probably have the approaches infinity, but no textbook at this level are you ever going to see that. They're going to go ahead and write the equals infinity, so you're welcome to do that as well. Now, what does this type of graph look like? Now, I'm not going to draw this exactly. I'm going to do a real quick sketch. Technically, what this graph looks like is this. Oh, sorry. That's not square. I didn't square that. All right, so here's what your graph looks like. We have a vertical asymptote at x equals 2. So here's the general idea, and I'm not going to draw it again, not exact, but as we approach 2, from one side it's heading up, and from the other side it's doing the exact same thing. So it looks something along those lines. It does, by the way, this does drop down across right there. I just didn't draw it completely exact. But there's the idea, right? As we come in from one side, it heads up. As we come in from the other side, so from both sides, it's heading towards infinity. So there we would say that that limit exists, and it goes towards infinity. All right, so when you're doing a limit towards a number, you always want to do direct substitution first. If you get 0 over 0, do some algebra, try factoring or rationalizing. If you get a number over 0, you got to look at both one-sided limits to see if those two things are equal. Now, so far we've looked at what happens to a function as we approach a number. But now let's take a look at what happens if we let the limit, instead of heading towards a number, a limit go to infinity. So here we generally say that this is called limits at infinity. So what if I said, what is the limit as x approaches infinity of some function? So the idea is, what happens if we let x get bigger and bigger and bigger? What happens to that expression? Well, let's start with a couple of basic ones here. What if I said, what's the limit as x approaches infinity of just 1 over x? Well, again, we're going to use a lot of reasoning skills here. If we take the number 1 and we divide it by a number that's getting bigger and bigger and bigger, that means that value has to be getting smaller and smaller and smaller, which means that this has to be eventually 0, right? It's getting smaller and smaller and smaller. Again, that should be approaches, but we generally say that that's 0. In fact, we can say that this is true. As long as x approaches infinity of 1 over x to the n, any power of x, that includes like radicals, right? Because remember, those are just fractional exponents. This would also be 0 as long as n is positive, right? If it's negative, technically that would come up to the top. Which gets us to this. What would the limit as x approaches infinity of just x be? Well, it's a silly sounding question. What happens to x as x goes to infinity? Well, this goes to infinity. In fact, what's the limit as x approaches infinity of any power of x? It's also infinity as long as that's positive, right? If it's negative, it would drop down and be this case up here. All right, so there's some kind of basics for us. Now, these are the most generic ones, but do you think it would matter if that was a 10 up there? 10 divided by a number getting bigger and bigger and bigger still gets smaller and smaller and smaller. So if you wanted to be 100% precise here, most textbooks will just use a 1. Technically, that's any number on the top, if you want. All right, so with these basic rules, we can actually take a look at what some of these things do. All right, I'm actually going to get rid of that for now. Let's take a look at the limit as x approaches infinity, x plus 3 over x squared plus 2x minus 4. All right, we're going to do this 2 different ways. I'm going to do it the way that the book's going to show you, an algebraic way, which takes a bit of algebra. And then we're going to do it the let's think about it way. And I think the let's think about it way is the best way to interpret a problem like this, which I'll be fine with you guys using on a test. Well, let me get this out of here for now. Here's the algebraic way. When you have a rational expression, take a look at the highest power you see. Notice x squared is the highest power. So what I'm going to do, I'm going to take the top of the rational expression and the bottom of the rational expression, and I'm going to multiply by 1 over the highest power. So I'm going to multiply by 1 over x squared. Now when I do that, of course I'm going to distribute that. That's x over x squared, 3 over x squared. I know this is looking awful, but it'll clean up nicely here in a second. X squared, 2x over x squared minus 4 over x squared. Now I'll move this up here. And then let's go ahead and reduce. So x over x squared is going to give me 1 over x. 3 over x squared, well, I can't do anything with that. X squared over x squared is 1. 2x over x squared would just be 2 over x. Minus, and I can't do anything with 4 over x squared. All right, now, we generally don't have to show this, but all the properties that we've seen in the past, we can just take the limit of each one of these. So let's take the limit of each one of these explicitly. So what would the limit as x goes to infinity of 1 over x be? Well, we just saw a second ago that would be 0. 3 over x squared, again, that's a number over a power of x, so that would be 0. On the bottom, that's 1, plus the limit of 2 over x, that would be 0, minus 4 over a power of x is 0. So this just ends up being 0 over 1, which is 0. So the answer to the original question, what's the limit as x goes to infinity of x plus 3 over x squared plus 2x minus 4? The answer is 0. Now, that's how you would do it algebraically, but I think that there's a lot easier way to interpret this. Let's start again. The limit as x approaches infinity, x plus 3 over x squared plus 2x minus 4. All right, now the whole idea behind what I'm getting ready to show you is based on your understanding of how big an infinity is. The problem is, as human beings, we can't even come remotely close to comprehending even the idea of what infinity is. Take the biggest number you can possibly think of. Something like this. Here's an interesting number, 10 to the 512th power. That right there, that number, and that's not even a particularly big number in the world of math, that right there is more atoms that are in the entire universe. So you took the entire visible universe and counted every single atom and everything you see, it's not as big as that number. Now take this number and raise it to 512, 512. Take each one of those, take that number, raise it to 512, whatever that is, raise it to that. And keep going. That number right there is so astronomically big, you couldn't even fit it in the universe if you tried to write it down. Now imagine doing this 1,000,000 times. That number, whatever that ridiculous number I just described is, isn't even close to infinity. So that's kind of what I mean by we can't really even understand what infinity is. All right, so let's think about this. Let's just look at the top. Let's look at the limit as x approaches infinity of x plus 3. As we head out towards infinity, this is going to be like a trillion plus 3. 100 quintillion, trillion, billion, zillions is plus 3. Is that plus 3 really adding anything to this quantity when we head towards infinity? Right? This is so insignificant compared to this that it's kind of like that doesn't even exist. And that's actually what we're going to be able to do. We're going to actually be able to treat it like it doesn't exist. In fact, let's just take a look at this. What about if I had the limit as x approaches infinity of this? Well, we just decided that that minus 4, right? 100 quintillion, zillion, zillion, billion, zillion squared minus 4, right? This isn't going to make any difference at all. So it's going to be like that's not even there either. Now, if we take a look at this, you're like, well, this one's growing too. But if you were to take a look at the difference between the graph of x squared and just the graph of x squared is our parabola that looks like this. That would be our line. Now notice we're still pretty close to the origin, and notice how much bigger this is than that almost immediately. So imagine how much bigger this is going to be than this when we get out there towards 100 trillion. Right? This is 100 trillion times 100 trillion. So that's 100 trillion, 100 trillions, and this is only 200 trillion. So this isn't growing at all compared to this, which means also it's kind of like that doesn't even exist. So really when we're dealing with rational expressions, all we got to deal with is a thing with the highest power on the top, that'll be dominating the top, and the thing with the highest power on the bottom, that'll be dominating the bottom. So what we do is you say, you know what, as x goes to infinity, this starts to look or act like the limit as x goes to infinity of just x over x squared. Right? Because all those lower terms aren't really going to be contributing anything as we get out towards infinity. Well, I can reduce that expression. That's just 1 over x. Now, there's something we do know, right? What's the limit as x goes to infinity as 1 over x? Well, that is 0. Of course, the same result that we got by doing all the algebra. So this is a very valid way of doing this. If you want to do it this way, it's fine. This can also help you memorize your rules for horizontal asymptotes from your pre-calculus class. I'll show you real quick. In a pre-calculus class, we generally had something like this. A sub n, x to the n, over there, and then some b to the n, x to the m, plus b0. Looked something like this was your generic polynomial. And then they gave you the rules like this. If n is bigger than m, or if m is bigger than n, certain things happen. Well, here's the idea. Since these are the dominating terms on the top, it's like all of that doesn't exist at all, right? So as x goes to infinity, what does this look like? Well, it's just a to the n, b to the m, x to the m. So what is the limit as n goes to infinity? Well, it kind of makes a difference, right? Now think about now, if m is bigger, when we reduce, kind of like what we did here, we still have x's on the bottom, which means this is going to do what? It's going to go to 0, right? So if m is bigger than n, this equals 0. If the top is bigger than the bottom, if n is bigger than m, Well, that means what? We'd have x's left on the top, so it would be kind of like this. We'd have like the limit as x goes to infinity of x squared. Well, of course, if x is going to infinity, x squared would also be going to infinity. So this would be infinity. And if n equals m, well, those two things would cancel, and what would we have left? We would just have a sub n over b sub n. Now, how does this relate to our horizontal asymptotes? Well, remember, we were trying to figure out what the y value equals to. So here we would have y equals 0, that was the x-axis. Here we'd have y equal infinity, so this would, since that doesn't really exist, this is no horizontal asymptote. And here we have the asymptote where it's just the ratio of the coefficients. So notice we can get back to our horizontal asymptote rule just by taking the limit as we head towards an infinity. All right, that's going to take a look at most of our limit things. However, we do have these weird piecewise functions that we've seen in the past, and we kind of got to treat them like their own separate problems. So real quick, let's take a look at piecewise. Can't write right now. Remember, piecewise functions are a function that has several different definitions depending on what piece you're going to use. So this is the definition of a piecewise function, or just a random piecewise function. Now, I'm going to give you a little bit of definition, a definition that's my definition, because I haven't really seen it in a textbook. Would you all agree that we use the function is x plus 3 if we're using values less than 1, and it's equal to 2x minus 4 if we're using values greater than 1. So at the x value of 1, we switch from one function to the other. So I'm going to say x equals 1 is what I'm going to call the switch point. Now, if you take the limit, if you're doing the limit as x approaches c of f of x, and x is not a switch point, treat it like a normal function. Okay, so basically here, if I said, what's the limit as x approaches 5 of f of x? Now in this case, since 5 is not a switch point, right? Our only switch point here is 1. Then really f of x is just defined to be what? This one, right? So in this case, this is really just the limit as x approaches 5 of 2x minus 4. So we could just do direct substitution. So that's 2 5s minus 4, which is 6. So if it's not a switch point, then just pick whichever function is defined at that x value and do direct substitution. However, if it is a switch point, if C is a switch point, you need to check both one-sided limits. Hey, here's what I mean. So let's say we did the same problem, limited, but let's head towards one of our function. See, here's some of the problem. You could argue this, you say, well, I can't plug 1 in here because it's defined at 1. It's equal to this at 1. But remember, a limit is the limit from the left and the limit from the right. Since this is defined at all values bigger than 1, it's continuous at 5. This may or may not be continuous at 1, so we may not be able to do direct substitution. So what we need to do is we need to take a look at the limit as we approach 1 from below and the limit as we approach 1 from above. Well, here's where this gets a little tricky. Now remember, 1 from below means values less than 1. So what does f of x equal when we're less than 1? Well, f of x is x plus 3 when we're less than 1. What does f of x equal if we're bigger than 1? Well, if we're bigger than 1, f of x is 2x minus 4. So notice, because it's at a switch point, we would be approaching that c value, our 1, from 2 different directions on 2 different pieces of the curve. That's why we need to break it apart. Now the good news, for each one of these, we can do direct substitution. So if I do direct substitution here, that's 1 plus 3, which is 4. Over here, that's 2 times 1 minus 4, which is negative 2. Okay, so since the limit from the left doesn't equal the limit from the right, right, these aren't the same, these don't equal, so we say that this limit does not exist. All right, so piecewise functions are a little bit different than other ones because they're a different type of function. If you're doing the limit of a piecewise function and it's not at a switch point, just do direct substitution. If it is at a switch point, you need to do the limit from the left and the limit from the right and compare those. If they're the same, then the limit exists and it's what it equals. If they're different, the limit does not exist.